Hello everyone, I am Afsin Islam, a PhD candidate from Swinburne University of Technology, Australia. It's a pleasure to be presenting my research today at the 14th International Conference on Mathematical Modeling in Physical Sciences. My presentation is titled Linking Climate Index Variability, Indian Ocean Dipole to Bushfire Risk Towards Improved Early Warning System for Victoria, Australia. In this study, I explored how variations in the Indian Ocean dipole, one of the key climate indices, can influence bushfire risk patterns across Victoria. The ultimate goal is to contribute to developing more accurate and timely early warning systems that can help communities better prepare for bushfire seasons. These are the contents I will be covering in the upcoming slides. Australia continues to experience increasing bushfire risk, mainly driven by prolonged dry spells and rising temperature linked to climate change. Recent studies have shown that large-scale climate indices such as Southern Oscillation Index, the El Nino Southern Oscillation, Indian Ocean Dipole Southern Annular Mode play a major role in influencing fire weather patterns across this continent. My research particularly focuses on southeastern Australia with a closer look at the state of Victoria, which has faced some of the most severe fire seasons in recent decades. The overall aim of this study is to develop a predictive model using artificial neural networks that can improve the accuracy and timeliness of bushfire early warning system, ultimately supporting better preparedness and response. The key objectives of this study is to understand how variations in the Indian Ocean dipole influence bushfire risk in Victoria, represented through the Forest Fire Danger Index or FFDI. Spatially, I examine both the spatial and temporal variability of this relationship across several weather stations and explore how lagged IOD phases, that is, the conditions from previous months, can influence fire weather in later periods. Finally, I develop an artificial neural network model to evaluate the predictive strength of Indian Ocean dipole on the Forest Fire Danger Index, aiming to improve the capacity of early bushfire warnings in southeastern Australia. This study is guided by three main research questions. First, how does variability in the Indian Ocean dipole influence bushfire risk, represented through changes in the Forest Fire Danger Index across Victoria? Second, what are the optimal lag periods? That is, how many months before a fire season the IOD exerts the strongest influence on fire weather conditions? And third, can an artificial neural network model better capture this nonlinear relationship and provide higher predictive accuracy than traditional statistical approaches? For this study, we selected 7 weather stations across Victoria, which have been marked in this slide. These stations were strategically chosen to ensure broad geographic coverage representing inland, coastal, and transitional zones from north to south. The selection was based on factors such as climatic diversity, availability of high-quality long-term data, and the ability to capture varied climate fire dynamics across different environmental settings. For this study, we used monthly climate and fire danger data from 1965 to 2019. The key climate input is the Indian Ocean dipole and the output is the Forest Fire Danger Index. The FFDI is calculated using temperature, humidity, wind speed, and drought factors. To study lagged effects, we used Indian Ocean dipole values from 1, 2, and 3 months earlier to predict future FFDI. All data were normalized, that means scaled between 0 and 1, and splitted into training, validation, and testing datasets following standard machine learning practice. We have used feed-forward artificial neural network for the modeling. This type of model is really good at learning nonlinear patterns, which traditional models often miss. For training the network, we have used the Levenberg-Marquardt algorithm, which is fast and reliable for this kind of task. We evaluated the performance using three metrics, the correlation coefficient, mean squared error, and mean absolute error. The entire model was built using MATLAB's neural network toolbox. So why lag matters? Bushfire risk doesn't appear overnight. Research shows that changes in climate indices like drops in rainfall or shifts in sea pressure often happen months before the fire season actually begins. These changes gradually dry out the vegetation and alter the weather conditions. That's why we explored 1, 2, and 3 months lag periods to identify how early we can detect the signals of fire danger. Using lagged IOD data helps us predict FFDI ahead of time, giving us a lead on potential fire seasons. If we can forecast fire risk even a month or two in advance, it allows emergency services to prepare equipment, allocate the resources, and issue early warnings, improving both readiness and response. This section sums up the strongest links between Indian Ocean Dipole and the Forest Fire Danger Index at 7 weather stations. We focused on where Indian Ocean Dipole gave the best predictive signal at 1, 2, or 3-month lag. The next slides show each station's best lag and what it reveals about changes in fire danger across space and time. This slide presents the 1-month lagged influence of the Indian Ocean Dipole on fire danger across the selected Victorian stations. We can see that the strongest relationship appear at Ballarat, where the correlation coefficient R is 0.93, where December Indian Ocean Dipole predicts January fire danger, followed by Mangalore, where the R value is 0.89, and Albury, where R is 0.88, both driven by October Indian Ocean Dipole, predicting the November FFDI. This means that positive Indian Ocean dipole phases during October to December tend to elevate fire danger in the following month. It highlights the Indian Ocean dipole's short-term predictive ability, particularly for early summer bushfire risk across Victoria. So essentially, monitoring Indian Ocean dipole behavior just a month ahead can give an early warning signal for potential fire danger peaks. This slide shows the 2-month lagged relationship between the IOD and fire danger. We can see that the highest predictive correlation occur at Albury, which is 0.92, Bearsendale, where the R value is 0.90, and Mildura, where the R is 0.902, indicating that Indian Ocean dipole values from November and December can predict fire danger 1 to 2 months later in January and February. This suggests that the Indian Ocean dipole's influence extends beyond short-term variability, maintaining a strong signal through late spring and early summer. In practical terms, this means that by monitoring Indian Ocean dipole patterns a couple of months in advance, we can anticipate elevated bushfire risk, particularly across eastern and northwestern Victoria. So overall, this 2-month lag highlights the Indian Ocean dipole's medium-range predictive capability, which is valuable for operational fire forecasting and preparedness planning. This slide presents the 3-month lagged influence of the Indian Ocean dipole on the Forest Fire Danger Index across the selected Victorian stations. As shown in the graph, most stations display relatively strong correlation even with a 3-month delay. The highest predictive strength are observed at Albury, which is 0.92, and Mangalore, which is 0.91, where November Indian Ocean dipole values best predict February fire danger. Ballarat also shows a notable correlation of 0.88, again linked to November Indian Ocean dipole predicting February forest fire danger index. What this means is that the Indian Ocean dipole anomalies detected in early spring can still influence the fire weather several months later. In other words, the ocean atmosphere interactions over the Indian Ocean retain their predictive signal well into summer. This highlights the long-lead potential of the IOD, suggesting that incorporating Indian Ocean dipole data into seasonal bushfire forecasting models could significantly improve the preparedness and early warning capabilities for southeastern Australia. To discuss about the ANN model performance, ANN models showed promising predictive capabilities, particularly for 2 months lag relationships. However, generalization remains a challenge, requiring further optimization to improve the model's robustness. So this and the following slides present the performance of artificial neural network models in predicting FFDI based on the lagged IoT values. The results highlight the predictive potential of climate-driven models for bushfire forecasting. For instance, at Albury, the model using October Indian Ocean dipole achieved a strong correlation of 0.88 when forecasting November FFDI, demonstrating the value of Indian Ocean dipole as an early indicator of fire danger. At longer now, the Indian Ocean dipole October model achieved an R value of 0.85, reinforcing ANN's capability in predicting December fire risk. These results highlight the importance of region-specific climate modeling. In this slide, we see that the Mangalore artificial neural network model performed exceptionally well with an R value of 0.91. This confirms that Indian Ocean dipole in November strongly influences the fire conditions in February, supporting extended climate forecasting. All these findings highlight the potential for AI-driven fire forecasting. By utilizing 2 to 3 month lagged Indian Ocean dipole signals, we can enhance the early warning systems and provide more accurate fire risk assessments. This research paves the way for integrating ANN models into bushfire management strategies to improve the preparedness and mitigation efforts. All these analyses reveal that Indian Ocean dipole values from October and November serve as the strongest predictors of bushfire danger, particularly for the summer fire season in Victoria. However, the strength and timing of this lagged impact were not uniform. They varied across different stations, suggesting that local climate and geographic factors influence how Indian Ocean dipole affects fire risk. Importantly, the artificial neural network models were able to capture these complex nonlinear relationships between Indian Ocean dipole variability and FFDI much more effectively than traditional linear models, highlighting their potential for improving the bushfire early warning system. Although the ANN performed well overall, some overfitting was observed during the validation phases at a few stations. For future refinement, the model could benefit from including other climate indices, such as the Indian Oscillation Index, Southern Annular Mood, to assess multi-index interactions. Additionally, incorporating more local weather parameters like the wind speed or humidity may further improve the regional prediction accuracy of bushfire danger. To conclude, this study demonstrates that Indian Ocean dipole variability has a strong and lagged influence on bushfire risk, with the most significant impacts occurring around 1 to 3 months before peak fire periods. The artificial neural network model successfully captured these nonlinear connections between climate and fire danger, offering promising potential for improving the early warning system. That's all from my side. Thank you so much for listening, and I'm happy to take any questions or feedback.